Welcome, welcome. Everything my way is stupid. Two, three. I should. 1, 2, 3, 4, 4. And I should see 1, 2, 3. 3 in one group. And
I'm in the second group.
yeah, and I will check. Maybe someone joined you. Nope, you're alone. Okay, 1 minute. Impossible things, all students. Something happened. I will make a recording. Just for recording. Guess what, no one wants to join us. You, I'm sure. You. Let's do something positive. Here. You know what people do when someone with phone and knows them finally? they take this form, large nail, and nail it to the wall. And place for information security. Okay, what I'm about today? Not about information security. I'm about today current and voltage sensor. See, the dog is digging. You have nice ideas, great ideas about your relays, about algorithms and about protection. But there is one tiny moment. Your signal is high current. I'm speaking about, not about amperes, about thousands of amperes. And under high tension. For high currents, I was near. What's this? Object. Appear in camera. See this object. What's this? Nope, it's not fuse. Maybe they are similar. Fuse. This is 1000 amp fuse. Yeah. It's really for 1000 amp. Double. See? Double connection. And what's this? It's so-called shunt or measuring resistance. It's a bigger brother of, for example, this one. 0.1 ohm resistance precise, rated for 5 amps. Yeah. Put 5 amps here, and you will get 5 multiplied by 0.1 volts here. Put 1.5 thousand amps here. This one is for 1.5 kiloamps. And you will get 75 millivolts here. It's a measuring resistance. Good thing, you can scale down your current. And sometimes they are used. But where the problem is? If here is, I don't know, 300 volts, it's not a problem. But if there is 300,000 volts, it's a problem. You need insulation between your tiny, small digital device and 330,000 volts. You need two things. You need downscale current, precisely downscale, and ensure insulation. It's not a trick for everyone to operate on thousands and thousands of volts, maybe even megavolts. What should we start from? Where should we start from? Name? This is current transformer. Secondary winding. Many turns of relatively thin wire, and primary, small amount of turn of quite massive wire. Current transformer. Our first choice is a current, here for example, current relay. I1, I2. Current transformers are manufactured only in two rated currents. Most are rated for secondary current being 5 amps. 80% or more for 5. Also exists version for rating current 1 amp. Mostly expensive models for high voltage. Typical have secondary current 5 amps. Primary may vary from small amounts. For example, this one is 50 to 5. Up to 100,000 ohms. Elements. Primary winding, steel core, and secondary winding. It's easy. What's not so easy? First, have you completed course of electrical machines? Yeah. How we analyze transformers in electrical machines? Transformer in electrical machine. No. What electrical machines? Why electrical machines? When you start your electrical machine, you have what? You have core, you have winding, you have EMF, yeah? And you have self-induction EMF of your winding, yeah? Of primary. And this, how to say, supplying EMF is in equilibrium with self-inductance EMF of primary winding, yeah? I'm correct? Yes, and why I'm not hearing it? Yes. This is nice model. It's nice model. Where are you? It's nice model for this transformer. It would be nice model for this transformer, and it's useless for current transformer. Useless. Because current transformer, okay. Here current is in 1000 ohms. Here 5 ohms. If we have 1000 against 5, what is transformation rate here? 200. If you have this load resistance, what will be? Reduction factor 1 to 100 square. You can do anything on secondary side. This will not change primary. You can do with your transformer what you want. Because here you have gigawatts. Your transformer will change nothing. And this means what model traditionally used in electrical machines will not work here. For current transformers, correct model is inductance of primary winding, resistance of primary winding, inductance of secondary winding, resistance of secondary winding. This can be to 5 amps. Load resistance, magnetic circuit, and all this power from power source. This is how correct model for current transformer looks like. It's powered from current source. Not EMF. Here should be. Load resistance, active resistance of secondary side, inductance of secondary side. Watch this. Now, what's the easiest regime for ordinary transformer? No load, yeah? When load is easier, no load. What about here? If I disconnect load resistance, what should be voltage here? If we are powering from current source. I can hear you. What will be voltage if load is infinite? Zero. Zero is marked as infinity. It's a current source. You can do what you want. Energy balance. On the one side you have gigawatts, on the other tiny transformer. Nothing changed. In theory voltage will be infinity, in real life something very high. Try to understand simple thing. The higher is load resistance, the higher secondary voltages, secondary side, to get the higher is voltage, the higher induction is needed. Understand it? You need higher. For in case of ordinary transformer, in case of short circuit, what will be flux in core? Simple transformer. What will be flux? And induction. 1/2. You completed course of vertical machines. 1/2. Short circuited ordinary transformer will have approximate drop in induction, core induction, 1/2. I can prove it. You can find theory of signals, magnetic circuits, and this video is available, and see it's in reality. I'm showing this experiment with short circuiting. So, easiest regime for current transformer is a short circuit. Really. Now, let's try what? Let's take our T means transformer, A means amperes. Designation for current transformer. Let's try to power it from control source and load with something, with some load resistance. Like experiment. If it would be ideal transformer, I would get something like this. M equals to I against ratio. What's the meaning of nominal in Latvian? Rated So if the M is a rating between real current and transformer's rated current. For example, this one, 200 amps. So here should be 200. Yeah. And this one, it will be primary current. Secondary is here 5 amps. How should it look like for ideal transformer? Yeah? With the scale, it should be wait, 1 divided transformer ratio. If here I have 2 turns and 200 to 5, what will be in reality? I1, I2. So in theory, I2 should be V1 divided by secondary winding and multiplied by I1. Yeah, it should be in theory. It's what physics tell. And what will be in reality? This is steel core. Maybe good quality, but anyway. What's the name of core? Sometimes. What's this called? Eh? Yes, it's steel core with saturation. So, if you do it in time, huh? Familiar? Name? Steel, hysteresis. Hysteresis loop. Up, down. HL, remaining magnetization. If you take family of all this loop, you will get something like this. It's a magnetizing chart of electrotechnical steel. Familiar something, huh? So it's in some books. What it's meaning, why it's for me? What's the meaning of this chart for us? This means, but in real life, you will get this one. It's for ideal, for spherical transformer in ideal world. Real one has a saturation. It's effective value. For protection, it's enough. 10% precision is enough. So I can put when points where the difference is 10%, and it's named M10. What will happen if I increase load resistance? I increase load resistance. real, this one is imaginary. So I'm increasing load resistance. What happens? To get the same current, I need high flux or high induction in core. Yeah? To get the same secondary current. I have primary current fixed. So to get the same secondary current, I need higher induction or higher flux in core. But I can't get, because this is reality. I will get something like this. And here, higher than, I will mark it blue, the higher resistance. This is this one is for increased load. If I decrease load, what happens? I decrease load resistance. Where point M10 shifts? To the right or to the left? Left? From where? If I increase load resistance, I will go here, and somewhere here will be my M10. Load see what happens? Point of precision shifts as a function of load resistance. Actually, you deal with something like this. Load. For each transformer, you have rated power. $50 to $5. This one has only 10 volt amps. This one, only 5 volt amps. You can convert it to load resistance, but actually you will get chart like this. It's an operation area of your transformer. Do not operation area of your transformer. If you fail to operate this circuit, if you overload your transformer, you'll be busted. This not appears until failure, until real fault. In case of fault, your transformer will be unable to supply current, will go outside of precision, and your protection will not trip, will not operate. Investigation shows it 100%, and you will fly out really. Remember this quote. I say it multiple times. You think many people understood? Come to me. And who is this?
Transformer.
Yes, it's a transformer. I can turn it like this. This one is for 10 kilovolts. But why is what's going in? See? Two cores. Why? One more massive from the raw, quite raw sheets. This one has a quite fine steel in it, and it's much smaller. This one is for metering, and this one for protection. This one for precision. This one for robustness. It can take much higher current load. This one measurement core saturates approximately at 1.5 of rated current. Its overload capability is only 50%. It's thin. It's deliberately done saturated because designs want to protect sensitive measurement, metering, and sensitive equipment from being damaged by overcurrents. This one should operate up to 40 time of rated current. So if rated current at 100 amps, this thing should operate up to 4,000 amps. That's why it's so messy, but it's not so precise. If you connect meters to this core, to protection core, you'll be busted. Because precision of this core, small, 0.2%, or even 0.1. High, 10%. Accounting, people responsible for accounting, metering, will simply skin you alive if you connect meter to protection core. And if you connect protection to metering core, you'll be far away from alloyed operation zone, because for this core there is no idea of M10, it's all idea of M.5. This core will saturate if current exceeds 1.5 of rated, and your protection will fail. What this mean? You busted. What this mean? Always check load capability of your transformer, what you're dealing with. If you put this, it's a measurement transformer, in protection circuit, it may work. It may work, but you should have very small consumption. Higher consumption and you busted. One who calling me also is busted. Yo, hello. No, копал за тварь.
Every time. Second test. What? This the second test. Last semester. Last semester. What? Last semester. No. We wait for his call. Then he will go. He will go saying back in 5 minutes and he goes. Akshay, are you attending next class? Are you attending next class? Right. Are we attending next class?
Today we are also up to
Always we have two classes.
T4.
Daily we have always we have two classes.
Oh, I don't know. But I can't.
If we skip, we will all will skip together. If we don't, we will not. We should have this thing. Not regularly.
We will talk. We can't sit till 4 o'clock. Saying thing.
If we don't come, then he will not study.
Yeah,
We should leave. That's on us. It's not Indian college. No, same.
We
Yes,
completed one subject. It failed.
same everything was same and we
Last,
cleared it.
but we were 3 passed.
Good, very fast.
Passed.
Can't they call him go?
Yeah.
3-4 we done.
Oh my God.
We talk.
How can I fill my timesheet? Just fill it. Okay, where am I? Overload of transformer. Regular checks do not open this problem. It's only flies out when you really in trouble, because it flies out when your protection fails. Okay. Core for protection, 10p. Core for metering. Precise but with small load capability, not so precise but with huge overload 40 times. With overload capability. Okay, transformer. Go back.
These are the children.
One transformer, two transformer, somewhere should be transformer number 3. Now, next problem. We spoke on how many transformer? One current, one transformer, yeah? One current, one transformer. 1000 amps, secondary 5 amps. 10 kilowatts insulation, everything fine. What's not fine? How many phases do we have in our network? 3, yeah? Let's start, maybe 6. Maybe 6. 5. I never heard on 5-phase network. I have one artifact. This motor is for 4-phase network. I saved it from the scrapyard, but it's for 4-phase network. Not 3, but 4. Some quite a long time ago, there were experiments in the United States with 6-phase network to increase transfer capability of the net. They attempted 6-phase networks. Our late Professor Chulichin participated in this. As I understood, ended with nothing. Okay, how DC are more promising. So, how can I connect my transformers in polyphase network? Version 1, I have A phase, phase and C phase, I will have transformer for A, transformer for B, and transformer for C phase. And I will have current relay for A phase, current relay for B, and current relay for C. Nice? The name for this is full stop. Grounding for safety. If there will be break in insulation, this grounding should take a hit. Current from transformer. Current through relay. Are they equal? Here, these currents are equal. To characterize connection schematics, special schematics rater idea is used. It's a relay current to the R current. In full start, schematics factor is 1. Everything easy here. Full start schematics. Full start and full start. Okay. Now take a look closer here. Can I draw it in yellow? What's this? A phase current, yeah? Will it flow in ground wire? Yeah. B phase current. And maybe in the red? Yes. So, neutral current is, oh, I should draw it yellow. A plus IB plus IC. In previous lection, what I told, you should be acquainted with symmetrical component. So, in terms of symmetrical component, what is it? Symmetrical component. Vectorial sum of phase currents. What's this? Name in terms of symmetrical components. You should understand symmetrical components. Vectorial sum of phase currents will give me what? sequence current is IA plus IB plus IC divided by 3. Yeah? So this one is a triple zero sequence current. If we do see a zero sequence current, what's the first idea when zero sequence current appears? We have Earth's fault. The first thing we should talk about if we see zero sequence current is an Earth's fault. If we have symmetrical load, what will be the value of zero sequence current? What can we expect? Huh? Smartphone addicts. We have normal symmetrical load. What will be the value of zero sequence current? No. Symmetrical load. Current in each phase 1,000 ohm. What will be zero sequence current? A phase 1,000, B phase 1,000, C phase 1,000. Zero. A phase plus B phase plus C phase should be 0. In case of ideal symmetrical load, zero sequence current is 0. In case of Earth's fault, what will be zero sequence current? Full current of fault. Plant a relay here, and it will have, in theory, 0 in signal in normal regime and full current of fault in case of Earth's fault. Earth's fault protection. This relay is very good, appears, to Earth's fault protection. ZSA, zemesloguma aizsardzība. Earth's fault protection. Current in the ground wire of full star at the first glance is a zero sequence current. Only triple zero sequence current. Triple I0. Very good for Earth's fault protection. At the first approach. For network which effectively Earth at neutral, it's true. But for network which isolated neutral, where can we make isolated neutral network? 6, 10, 11, 24, something like this. Not everywhere. Some use isolated neutral, some not. If you have a single phase bar, it's easy. You drive along the road and look at transformers at customer. Here you can find transformers. They are hidden. We don't use single phase transformers. Except railroad. Railroad use single phase transformer. You cannot find things like American style, where each customer has its own transformer. If you have one high voltage terminal on transformer, this is earth at ground network. If two, it's isolated. Appears what you'll hear about network regimes first time in your life? Eh? What there is isolated and grounded neutral regimes. Where am I? What I'm doing here? I need another planet. Okay, I'll tackle it in Earthfall protection. Here. Okay. I'll draw one thing. Grounded neutral. Customer can be customer connection and grounded network. Possible. Isolated neutral. Good idea. A, B. C. Use delta at net side. Delta or zigzag. What's connection of this transformer? Yes, it's a three-phase transformer. But what's the connection?
Star.
On which side? Here is primary side, here is secondary. What's the connection on primary side?
Primary delta.
Delta and secondary?
Star.
Star. Yeah. Same thing. Here can be 10, 11, I don't know, 13, 24 kilovolts, something like this. There is no need for single phase. What's good in such network? Why? Because if you have an earth here, current is limited by capacitance. You can keep operate. Auto regulation allowed 8 hours of operation with earth fault. You need to find it and solve in 8 hours. Now it's more problematic in rural areas. Yeah, you can do it lazy. But in cities, because company don't want to pay damage if someone gets you need to disconnect in inhabited areas. And we face problem. What's the current of earth fault in isolated network? I don't know. Actually, auto regulation required to limit current in 15 amps. Earth fault current in distribution network, auto regulation asked to limit it with 15 amps. If higher, something needs to be done. Here in Riga now this current will be 1000. It's local city regulation. Earth fault current cannot exceed 1000 amps. And we will see one problem with earth fault protection for distribution network. This one theoretical example. connection like this. A, B. Oh, it has its name. It's a Holmgren. It's Holmgren schematics. What do you see? Full stop without phase relays. So it's pure for triple zero current. It's like transformer connection for earth fault protection. This Holmgren schematics is very useful to understand one problem with earth fault protection and current transformers. Let's assume symmetrical load. EA equals to IB equals to IC. In magnitudes, angles are 2/3, so symmetrical load. True symmetrical load. Schematics. L1, L1, L2, A2. Current transformer. This is schematics for A-phase current transformer. To simulate symmetrical load, I will power it from current source. Phase B, L1, L1, L2, L2. A square. What is A square? I mean the terms of symmetrical components. What's the meaning of A square? I asked you to be acquainted with symmetrical components. A is a rotation operator. A equals A power dot 2/3 P. A square, it's a rotation 240 degrees or A 2/3 P. To get B phase, I need rotation 230 degrees. And this will be phase C. Or here it's a red phase. This is B, this is C, connected, load resistance, and here goes return, ground. Here is Holmgren schematics. In case of symmetrical load. Current here. Yep. Path will flow to magnetizing circuit. So this current is A. This one is A square J minus E mu B. And from here goes A minus E mu C. What will be current through load resistance? So E neutral equals to your 1 plus A squared minus E mu A plus E mu B plus E mu C. Yes? Is it correct? What will I get here? From this sum? Basics of polyphase networks. One A, this is 1, this is A, this is A squared. What will be sum of them? One A squared. Sum of them. 0. Yes, exactly, 0. So in case of symmetrical load, this will fall. It's called non-balanced current of Holmgren scheme. If we would use ideal transformer, this current should be 0. In reality, even with sequential numbers, you take one model, same model, not only same rating, same batch of production, transformers with sequential numbers. Anyway, there will be a difference. There are no absolutely uniform current transformers in this world. Bit different assembly of core, bit different steel. Even you take one sheet of steel, it will be thinner on the side and bit thicker in the middle. Because the rollers of the roller press were like this. Sometimes roller press are adjusted a bit incorrectly, and they press like this. So this means that one side will be thick. Thermal processing may be different. Even roller sheets are not uniform. They have different magnetic conductivity alongside of rolling and crossing. All transformers are a bit different. Manufacturers guarantee that this difference do not exceed 10%. So you always will be inside toleration area. This 10% actually toleration areas may look like for manufacturers sometimes give you this as toleration area, error in percent, area of error operation. Anyway, non-balanced current is inside 10% of primary. It's okay for network with high fault current. But what about isolated neutral network? Earth fault current 15 amps. Primary rating 1 kiloamperes, 2 kiloamperes, maybe 1.5 kiloamperes. Feel the difference? Yes. for isolated neutral network, this limits, seriously limits effectiveness of Earth fault protection. Simple, non-balanced current simple puts a cap on your sensitivity. Non-balanced current for 1000 ohm transformer is 100 ohm. Earth fault current 15 ohm. No, somewhere 10 times. Yeah, it's a problem. Home grids in work do not work in isolated neutral network case. What to do? How to get? Come here. Solution is here. Case. Solution to your problem. In local argo, it's a Ferranti transformer. Special transformer in two parts. It's so-called cable transformer. Take your high voltage cable. Take your cable. This is simple cable. And what to do? You need to do like this. Your cable should go through this transformer. Usually. They add a bit lower here connection, and in lower, a bit lower, this transformer. What's the idea? Why this transformer is better than this one? Why it's better? Where the non-balanced current comes from? From the difference of magnetizing characteristic of transformer cores. To overcome idea. A phase current, let's say B phase and C phase current. This is core of my transformer. This one has a splittable core. Older models have monocore, and if you forget to put cable through transformer before making this job, before putting an end to cable, you seriously, you in problem, because you need to cut cable and put a joint outside of visible path. You dig outside of substation, cut it here, walk through transformer and put a joint in earth. So construction supervisor don't see. But where the trick is, we have three currents here. For each current there will be a flux flux. This is my winding. What flux goes through this winding? Vectorial sum of A, B, C equals plus flux B plus flux C equals to triple zero sequence flux. Here are winding terminals. Through this winding goes triple zero sequence flux. Non-balance is a result of core nonlinearity. Non-linearity is between ampere turns and induction. Here everything is uniform. This transformer may have bigger error than phase, but it will not have non-balanced current. Triple flux, and here will be non-balanced current from transformers expected 0. There still will be some current because network itself is not symmetrical. Capacitance against ground is not uniform, but it's much smaller. You will get your sensitivity. Without cable transformers, earth fault protection, no, not the protection. One thing, you have a screen here. Yeah? What this tail is from? From the screens. Cables are screen. Some have has external armor. Screen. Cable. This 20 kilovolt cable. Here, screen comes out. Okay. It's screened. Copper wires and foil outside. They go free together through transformer. What will you do with the screen? Yes, it should be earth. One of the terrible mistakes do like this. Why? Because in case of some external fault, this current will flow towards substation. Transformers start centers are grounded at substation, grounding, field or substation grounding. So current through screen will go to transformer and you will see what? You will see fails earth fault. Your protection will trip. If someone makes this mistake and I know, I will go to jail, but I will hit you until urinates with blood. I will kill for this. Right earthing. Earthing wire from the screen should go backward through transformer. If not, dig your grave. I will not live with this honor, but my students make this mistake, so dig your grave. Backward through transformer. So this current flows backward and there will be no fails. This short tail will not work. You will need to connect them together, put a common wire, it lasts 25 square millimeters, and pass through transformer. What did you create? Seriously. Earthing cable should go back through transformer. All protection will fail. One more mistake, I will kill for. A-phase transformer, B-phase, C-phase transformer. Safety grounding. Start connection, return wire. Neutral relay channel. A, B, C phase. ABC is okay? Or you're familiar with RST? What's a common designation in your account? ABC or RST? RST? ABC or RST? Wait. Yeah, or opposite sequence. Red, yellow, blue.
And green.
And green.
Yeah.
See? Yellow, blue, red. We had order. Very simple, but A was yellow,
Yeah.
B green, and C red. A, B, C, R, S, T, and
RYB.
red, yellow, blue. Also, we do double. Okay, it's A equal. I'm an old monkey, I will write ABC. This red, yellow, blue, damn, we have yellow of A. Sometimes I reprogram devices to show.
ABC.
Not ABC, but in our case should be yellow, green, red. Red in our old system, red was C phase. Our old system was yellow, green, red. Now at this time buses are painted yellow, green, red. ABC. A, B, C. It depends who first started. If guys like Siemens, it will be ABC. Siemens Galsky in its export version. In its internal version, it will be RST. And RIB someone from General Electric. And frequency 60 or 50? 50. The best life in Japan, northern Japan 50, southern 60. And virtually no interconnection. And different sockets.
How does a frequency depends?
No, it's a quite a long story. Very few people knew it. First, see, in Europe there was everything started at the point when Niagara project was started. Guys from Westinghouse received an order for hydrogenarators. And they had a very nice project, 50 hertz for common supply for lighting, 25 for electrical traction, and also 12.5. They were unable to produce locomotive motor, AC locomotive motor for higher frequency. They had a very nice design, and mother of this design, Westinghouse saw a Siemens generator for 133 Hz. They downscaled it to 50, it was a quite round number, everywhere were happy. Until one nice day, main company, Cataract Project, informed Westinghouse, you know, we already ordered the turbines for 250 RPM. At this moment, Westinghouse opened their eyes widely and understood 20 kilovolts, two-phase. At this time they designed a two-phase machine, two-phase, not three. For such condition, will simply destroy the building, it will fall down. So Niagara Falls will simply collapse because machine will be so heavy and will have so terrible load on the ceiling between water chamber and generator itself. But it's simply not possible to build. And they, as fast as possible, redesigned it. And closest what they can get was 60. Set 60 Hz for lighting and 60 divided by 4 for traction. At the point where the 60 Hz emerged. Because Cataract Project ordered turbines which were not suitable, too fast and not suitable for 50 Hz machines. So Westinghouse was happy. It's near disaster because financial it will fall on Westinghouse company. Yeah, so they choose 60 Hz and United States and everywhere. There was a moment when financial institutions, banksters forced Westinghouse and General Electric to interchange patents for bulbs and so on. Both companies were on the brink of bankruptcy. So debt owners forced them to interchange patents. And everything becomes, in the United States, becomes 60 Hz. And in Europe, Siemens worked with original 50 Hz design. They were not forced by these Niagara Project turbines. They were not limited. Okay, where am I? Yeah, I'm about mistake. This is good network, where you can make a terrible mistake. This would be terrible mistake. Put an Earth at a star on the opposite side. Why it's a mistake? Why I will have serious intention to kill you for this. Because in case of some absolutely foreign fault, current of this fault will flow through relay and cause false strip of protection. Never ever in any case create a double earth. Seriously. It called the guys who did it and false strip occurred. If I know what you did, dig your grave. It's one of the terrible mistakes what can be done. One more terrible mistake, you know how people disconnected all center of London. They changed transformers without changing trip current on railways. Everything was well until one of the cable needed repair and all load was put to second one. These morons mixed 600 and 400 amp transformer. As a result, fell strip and it was impossible to reconnect. At the moment, this patch call repower, protection trips, and again nothing. It was disaster. So, no double earthing. It's a serious crime. Okay, I think we should take a break. Yeah? And then I will continue. I have more about transformers. Okay, I will end the stream now. We have 2 lectures for today, yeah?